So we have seen how large-scale structure is supposed to form, theoretically, but now let us take a look at what observations have to say. The basic paradigm, of course, is that density fluctuations from the early universe collapse into structures that we see today, and that formation continues through hierarchical merging of smaller pieces into ever larger ones. So clearly we distinguish between galaxies, which are obviously seen as unit things in space, and they're dissipatively formed structures, achieving density contrast of the order of million relative to the average density, which clearly puts them apart from large-scale structure itself, consisting of assemblies of really dark matter with galaxies used as tracers. So by the large-scale structure, we talk about galaxy groups, filaments, clusters, sheets, superclusters, and that is what we will be addressing now. Note that the basic assumption here is that we do know that most of the mass is in form of non-baryonic dark matter, and that most of the baryonic matter we don't really see directly. So we hope, and this turns out to be actually a pretty good assumption, that galaxies, visible ones, trace the large-scale structure that's actually there in invisible material. The basic way of quantifying large-scale structure is to first map it out, find out where all the galaxies are, and see what their density field is like. To do this, we obviously measure two coordinates in the sky, and we need a third radial coordinate. This is obtained through redshifts, assuming, of course, that Hubble expansion works. So we need to do large redshift surveys, measuring redshifts for as many galaxies as possible in order to trace the large-scale structure. It was recognized already in the early 20th century that galaxies are not randomly distributed in space, but rather they seem to congregate. However, it took until about 1970s to really start quantifying this. So in 1930s, Shapley and Zwicky, who started first systematic sky surveying, noted that galaxies do seem to form large structures. Shown here on the left is one of the contour maps of projected galaxy densities on the sky from one of Zwicky's atlases. The quantitative analysis of galaxy clustering started in the 1950s by Shane and Virtanen, astronomers who counted galaxies per unit area on photographic sky plates taken at Lick Observatory. Those so-called Lick galaxy counts turn out to be a basic material for a lot of the early theoretical studies of large-scale structure. From 50s through 1970s, more and more attention was paid to it. Gerard de Vaucouleurs in particular noticed what we now call the local supercluster, and more galaxy redshift surveys were conducted. The redshift surveys really came into prominence in the 1980s and beyond. And today we have redshifts for maybe 2 million galaxies or so. Here is a simple projection on the sky of the 6,000 brightest galaxies. Two things are immediately apparent. There is the belt where galaxies are absent, and that's called the zone of avoidance. We now understand that this is due to the interstellar dust absorption in our own galaxy, that we simply cannot see very much through the dusty interstellar medium in the Milky Way's disk. Outside of that, you see that there is some structure. Now, if you were to make a plot of 6,000 brightest stars in the sky, it will be exactly the opposite. They'll all concentrate in what is the zone of avoidance of the galactic world, I mean the disk of the Milky Way, and otherwise they'll be fairly randomly distributed on the rest of the sky. So here is the 3D picture of our immediate extragalactic neighborhood, the so-called local group of galaxies. Milky Way and Andromeda are the two dominant galaxies in the group, and there is a large number of their dwarf galaxy satellites. Groups of galaxies are indeed where most of the galaxies are, so they're the most common building block of larger scale structures. We mentioned the local supercluster earlier. This was noted as an elegant structure in the sky, and that we are kind of in its plane. The center is on Virgo cluster, the nearest cluster of galaxies to us, and it's roughly 60 megaparsecs in scale. As superclusters go, this is not a very large supercluster, but it is the one in which we belong. In addition to the commonly used equatorial or ecliptic or galactic coordinates from astronomy, we now define so-called supergalactic coordinates. The xy plane of the supergalactic coordinates is the plane of the local supercluster, and we are at its origin, and vertical z direction is orthogonal to it. Later on, we will see plots of some of the distributions projected onto this xy plane of the supergalactic coordinates. So here is the rough 3D sketch of what local supercluster might look like. This plot is centered on a local group of galaxies, but really the center of the local supercluster is at Virgo. The rest of the structures are various galaxy groups or individual galaxies. Actually, there are very few isolated galaxies. Most of them are in groups. It is not a perfectly flat system like the disk of the Milky Way, but it is flattened. Two other clusters that are sort of peripheral to the local supercluster are Fornax and Eridanus. They're sort of on the other side of the sky from Virgo. Now this becomes a little more apparent if we plot not 6,000 but 15,000 brightest galaxies in the sky. This was typical of galaxy catalogs until, say, 1990s, where those were galaxies selected by eye on photographic sky survey plates. Here you can see that there is a great circle shown here through these arches that does go through a lot of galaxies, and that is indeed the plane of the local supercluster. To the upper left, sort of, you see a structure called Centaurus or Hydra Centaurus. This is another supercluster of galaxies, and in fact it's bigger than local supercluster, and we're falling to it. We'll talk more about that when we talk about peculiar velocities. On the other side is Perseus Pisces supercluster, roughly at the same distance. So superclusters themselves tend to form slightly more coherent structures. And this is not surprising from everything that we know about large-scale structures. So the mapping of large-scale structure begins with catalogs of galaxies on the sky. And those were counted by eye, well, originally by Messier and Herschel and so on. But really, the more modern ones begin with Shapley and Ames in 1930s, and then Lick galaxy counts in 1950s. And there are famous catalogs like Uppsala General Catalogue of Galaxies and its southern extension. Still, the Shane-Bertanen Lick counts were the largest up until the 1980s. They counted close to 1 million galaxies in the sky, which is why this was a good statistical sample for early studies. The next step came with digitization of sky survey plates, and that was done for both northern and southern sky starting in sometime in late 1980s, and APM is for Automated Plate Measuring Machine in Cambridge, England, and people who then did this work produced a catalog of roughly 2 million galaxies. The northern version of it from the second Palomar Sky Survey, so-called Digital Palomar Observatory Sky Survey, or DPOS, counted about 50 million galaxies. By mid-2000s, Sloan Digital Sky Survey obtained much higher quality data for a couple 100 million galaxies at first. Nowadays, they all have almost 1 billion, both stars and galaxies. In the future, we'll look towards even larger sky surveys and Large Synoptic Survey Telescope, or LSST, which certainly will not be completed in 2015. This is an old slide, more like 2020. We'll probably map billions of galaxies. But that's just pictures on the sky. In order to get the third dimension, redshifts are needed. And the first modern redshift survey was probably the one done at Harvard-Smithsonian Center for Astrophysics in mid-80s. They obtained redshifts of the order of 1,000 nearby galaxies and started to quantify large-scale structure near us. Along with its southern extension, they covered of the order 2,500 galaxies. This was already good enough to begin first modern quantitative structures of galaxy clustering. Now, you may recall the zone of avoidance was placing this artificial belt of missing galaxies in the sky, simply due to the extinction in our own Milky Way. The way to bypass this was to look in infrared, as infrared light goes through interstellar dust relatively unobscured. By mid-1990s, there was a good catalog of infrared selected galaxies from the All-Sky Survey by IRAS satellite. That produced a fairly unbiased set of galaxies that enabled astronomers to go deep into the zone of avoidance. The resulting redshift surveys now went up to 9,000 galaxies. And buoyed by their initial success, the Center for Astrophysics conducted a second-generation redshift survey, which compiled redshifts of about 25,000 galaxies. John Huckra was the leading astronomer in that enterprise, and also his collaborators, including Margaret Geller and others. Roughly at the same time, Carnegie Observatories did Las Campanas redshift survey in the southern hemisphere using one of the first modern multi-object spectrographs, and they obtained redshift for comparable number, about 23,000 galaxies. These surveys of 1990s started revealing more interesting features in the galaxy distribution, but really the state of the art was achieved by two large surveys, one in Australia, the 2-degree field redshift survey, and the Sloan Digital Sky Survey. We'll talk a little more about them later, which together now mapped well over 1 million galaxies. Let's now look at the sky in successive redshift shells as we step out. The closest one will be shown here. This is galaxies with recession velocities due to the Hubble expansion up to 3,000 kilometers per second. And the biggest feature you see is the local supercluster. Most of the galaxies being centered on Virgo, but with some pieces in Fornax. And stepping further out between 3,000 and 6,000 kilometers per second, new structures come in. The most notable one is the Perseus-Pisces supercluster, opposite from Virgo. This was largely done by Giovanelli and Haynes at Cornell and their collaborators, who conducted their work in parallel with the CFA group. And again, sort of opposite to Perseus-Pisces and almost hidden by the galactic plane is the Hydra-Centaurus supercluster, which later made an appearance under the name of Great Attractor, but we'll talk about that later. And now even further out, between 6,000 and 9,000 kilometers per second, the biggest feature is the Coma Ebel 1367 supercluster, composed largely of these two rich clusters. But there are also some vestiges of others, especially on the Perseus-Pisces side. And so here is a 3D sketch of what our local supergalactic neighborhood might look like, with local supercluster and nearby superclusters like Perseus-Pisces and Hydra-Centaurus. You've probably noticed that superclusters, at least those near us, are given names by the constellations in which most of the galaxies are placed. Constellations, of course, have no physical meaning, but they're still used as a traditional convenience to designate where in the sky some things might be.